Hi students, see I am discussing semiconductor chapter. So we are here for semiconductor discussion. I will give this video clip in 2-3 parts if possible, so that we have an advanced preparation for the next week topic. See, our major entry into this chapter starts with the classification of materials. I am repeating, our major entry into this chapter basically depends on classification of materials. What exactly does the classification stands for? I think you can see here. You can see here where I am sharing you the screen. I have classified the materials into 3 categories. I am speaking about a solid here. The materials which we know right now in the form of solid are basically classified as conductors, insulators, semiconductors. We are having a clear idea about these two till now because majority of our electrodynamics is related to those areas. In conductors, majorly we observed number of free electrons per unit volume is a high, low resistance, high conductivity, temperature sensitivity. Alpha is temperature sensitivity factor. I should say temperature coefficient of resistance. Temperature coefficient of resistance. Temperature coefficient of resistance is positive, means on heating with the rise of temperature, the resistance or resistivity of this material will increase. More or less, you find the same situation in insulator, only difference is in insulator, what you will notice is you have a very few electrons, means the number of electrons per unit volume is less for conduction. And that is also termed as high resistivity. Because the resistance is high, it has low conductivity. See, insulators, majority of the insulators will have alpha negative. With the increase in temperature, alpha is a negative such that the conductivity increases. See, try to please understand why it is so. I'll explain. You already have studied in current electricity. Resistivity factor depends on 2 things. One, it is inversely proportional to number of free electrons per unit volume, and it is also inversely proportional to relaxation time. Tau. Tau refers to the average time interval between any two successive conditions. In conductors, there is no huge effect on N, but the relaxation time factor decreases because of the increase in amplitude of the atoms or molecules linked to the particular lattice positions. So tau decreases, rho increases. Whereas in case of insulators, of course, tau effect is there, but the domination is more with the N. The moment you increase the temperature, N also increases. The domination of an increment in N subsides the decrement in tau. So therefore, effectively, resistivity decreases. And hence alpha is negative for these 2 materials. Semiconductors also, very few. See, insulators, very few, undoubtedly. Semiconductors, few free electrons. and their resistivity lies between conductors and insulators. When resistivity lies between conductors and semiconductors, similarly conductivity. So the very big significance of insulator is that basically uh, marginal rise in conductivity is noticed. But in case of semiconductors, a huge amount will be noticed. That is the reason why only conductors will accept Ohm's law. Semiconductors will not follow Ohm's law. Means voltage and current curves are not straight lines. So to study much more carefully, we require band theory in solids. Band theory in solids. Remember, the band theory in solids is based on Pauli's exclusion principle. See, if we are taking an isolated atom, in an isolated atom, the electron present in a specific energy level is as per the quantum mechanical laws. Like for example, you take a material whose atomic number is say 10. So 1s2, 2s2, 2p6. This is how the electrons were distributed various orbitals. The energies of electrons in a free electron cannot have any arbitrary values. I am speaking about an isolated atom, an electron in an isolated atom. They cannot have arbitrary values, but their energy levels were quantized. So it will have a defined energy level. Fine. What about the same situation in case of a solid? When I am speaking about a solid, you will have nearly 10 to the power of 23 to 10 to the power of 26 atoms per unit one. Now what happens? For example, a particular isolated atom, which we have discussed right now, say for example, 3s2, 1s2, 2s2, 2p6, 3s7, say for example, 11. That one electron under isolated condition will have a definite energy, unique. But when you have 10 to the power of 26 atoms in a unit volume, what will happen is that particular energy level is divided into 10 to the power of 26 closely spaced energy levels. I'm repeating. This 3s1 electron, which was supposed to have a definite sharp energy level, is now divided into 10 to the power of 6 closely spaced. Hello. హెల్త్ బాగాలేదండి ఇవాళ. అందుకే మధ్యాహ్నం ఎగ్జామ్కి వస్తాడు. వామిటింగ్స్ అవుతుంది పొద్దున్న నుంచి. వామిటింగ్స్ కంటిన్యూస్‌గా పొద్దున్న నుంచి 3 టైమ్స్ అవుతాయి. రైట్. So now this 3s1 electron will be divided into 10 power 26 closely spaced energy levels. For your understanding, say for example, I'm just giving you for example. So that particular electron will have a sharp value of 2 electrons. Now somewhere 1.999999 decimal के बाद 26 digits. 2 2.0000 somewhere decimal followed by 26 places. Likewise, division takes place. They are all close to 2 electron volts only, but not the same energy level, different energy levels. So, closely spaced this distinguished energy levels all together is called a band. It's called band, a collection of closely spaced energy. Remember, when I am saying this modification is not applicable for the electrons which are close to the nucleus, which are called inertials, which were completely filled. All these observations are mostly applicable for outermost shells. See why modification is applicable? Because the electrons are shared by many neighboring atoms. So, what was used to be a discrete energy level will now split up or spread out to form energy bands. The quantity of these energy level depends on the quantity of interreacting atoms. So, which means a sharp discrete energy level now splits into, if I say 10 power 23 are available per unit volume, then you will find 10 power 23 levels closely spaced across the 2 electron volts. Otherwise, I'll tell you, the energy level difference between one level and the next immediate level is of the order of 10 power minus 23 electrons. So such closely spaced energy levels is what we will call now as bands. So I have tried to give you a correct and proper explanation for what I have said. Don't worry, I'll post the notes. So I'll post the notes and you can take a printout of this, right? So what now energy band refers to here? When you say an energy band, the energy band here refers to range of energy. Whose energy? These are the energy possessed by electron in a solid. Or in other words, energy band refers to a collection of closely spaced energy bands, energy levels. I'm telling again, the difference of energy levels is of the order of 10 power minus 23 electron volts. Right. Now, on the basis of this, we will decide or we will classify materials into 3 categories on the basis of energy band structure. One, a conductor. Energy band structure. So this is a conductor. Next, the other part is a semiconductor. A semiconductor. So I'm avoiding writing part and want to increase the um, insulator. You can see the clear difference. I hope I have reached you. See, usually the gap between conduction band and valency band is usually called as, just give me some space otherwise. Because space is important for me. So usually, as per band theory, you will classify a solid like this. You will classify a solid like this. And this gap is called forbidden energy gap, which we will write it as a delta Eg. Delta Eg is nothing but the minimum energy level corresponding to conduction band to the maximum energy level corresponding to valency band. The energy gap is such a concept where you don't find an electron that has a specific energy in that zone. That is the reason why it is called forbidden. So in this, you will have no free electron exists. See, the width depends on nature of substance. Nature of substance. If you are speaking about a more width condition, valency electrons are strongly attached with the nucleus, like your insulators. Right. Of course, with the increase in temperature, if the temperature is increased, the gap decreases slightly. It is a general picture. What I am taking right now is a general picture. Now we will take conductors. In conductors, you see valency band overlaps with the conduction band. So there is no energy gap, which means a higher energetic electron in valency band with a normal room temperature condition will be into conduction band. Whereas the semiconductor, you see the energy gap is small. For example, if you take silicon, the silicon will have an energy gap of 1.1 electron. Germanium will have 0.7 electron. So the band gap is small enough that at room temperature, an electron in valency band can jump into the conduction. So gap is small. I'll go with a very detailed discussion. In insulator, you see the gap is high. It's more than 3 electrons. Next. Now, one more important point is, at absolute zero temperature, okay, no electron, I'm speaking about absolute zero temperature. No electron has energy to jump from valency band to conduction band, and hence in this stage the crystal is an insulator. At very low temperature, a semiconductor behaves like an insulator. At room temperature, you take 25 degrees, 30 degrees centigrade, etc. Some valency electrons gain energy to cross energy gap, right? And this makes the conduction band to fill with electrons. Therefore, on the basis of which now we will classify materials into 3 categories. And just a rough hint will be given to you, which, if required, you need to remember. This part you need to remember. Next. Now, what is happening in a conductor? When you maintain some potential difference in a conductor, what is happening? The electrons, free electrons will be drifted, and that gives rise to current. In a in a particular solid, what is happening is, by maintaining potential difference across the ends, conductor potential gradient will form, and that will drift the electrons. So majority of conduction is due to free electrons. That's it. Whereas in case of semiconductors, in case of a semiconductor, in case of a semiconductor, now if we have a valency band like this, here we should assume some energy levels, in a valency band, some energy level. I'll mark it like this. You take some energy level. Just win only 2 lanes. That doesn't mean these are the only 2 lanes available. And this is the conduction band. Again, the conduction band contains some energy levels. Lines represent some energy levels. Now the question is, an electron, when jumps from here to this level, it leaves a gap. This is called hole, and this is your electron. So whenever an electron, I'll clearly explain later. Whenever an electron jumps from a level in valency band to a level in a conduction band, you will have an electron in that conduction band, it leaving a hole in valency band. So this is important. And not only that, if you go through the energy band structure, the energy band structure, this is how you will have the energy band structure. So remember, all these things comes under conductor. All these things comes under insulator. Whereas all these things will come under insulator. I'm just showing you the difference. Now we will go with proper understanding of a semiconductor. What is happening in a semiconductor? What is happening in a semiconductor? See, usually silicon or germanium will have an electronic configuration. The valence state configuration is ns2 np2, which means it will have 4 electrons, which forms 4 bonds. 4 bonds, like what I am showing in a figure. Plus 4 indicates the valence is 4. This is in purest form. This is also called as intrinsic semiconductor. This is also called as intrinsic semiconductor. So at absolute zero, so what you will notice here is you will notice that you will notice the following. All the covalent bonds are complete and no free electrons. And no free electrons. The second point is valency bands are completely filled. When this is completely filled, conduction band is completely empty. At this stage, it behaves as an insulator. All that which I have discussed is at 0 Kelvin. Don't forget. Now, what is happening at the room temperature? Now, at room temperature, what happens? I will describe it with diagram. So, at room temperature, say 300 Kelvin. So, at this stage, what will happen is, now temperature provides the sufficient energy for an electron in the covalent bond. For example, you can see in this site, it is already in bond. So this electron here now sets free. Remember, just because of this process, it creates a hole here. Hole always represent electron vacancy. And this is thermally generated free electron. Now, where will be the location of this electron? Now, this electron will be, now what will happen here? I'll write stepwise. Some of covalent bonds are broken. Clear? Due to thermal energy, you will have a very few free electrons in valency band, in conduction band here, and valency band are partially empty, not completely, partially empty, and contains holes. Similarly, conduction band is partially filled. Now, this happens at room temperature, and this can also be shown in the band structure like this. In the band structure like this. Here, the red dots represents electrons. The white dots represents holes. Please note that holes are strictly in valency band and electrons are strictly in conduction band. Holes are almost at the highest energy state of the valency band. Electrons are at the lowest stage of the conduction. But whatever it is, they are free electrons. Now, because of which conduction takes place. And this behaves better when compared to the earlier state. Now, what will happen is this process, what I have described, is what we will call as electron hole pairing. Now, what will happen is, see, try to understand at this stage, what is happening. At this particular state, what we notice is energy is received by this electron in the bonding and covalent bond breaks and it is free to move in the crystal lattice. While it comes out of the covalent bonds, it behaves, it leaves a vacancy which is called a hole, and this process is called, and in this process is called electron hole generation, which I will mention here. Remember, this is a very important term. Electron hole pair generation. Right. See, both electron as well as hole, they will move randomly in the crystal. Or otherwise, the holes also move . randomly in crystal. Now you may ask me, how is this possible? I will explain. I'll explain. Now, for example, if this hole is filled by another electron in somewhere in the covalent bond, this hole is filled with the electron and a fresh hole is created there. So which means we can assume this hole is shifted to that lattice location. So therefore, what is that I'm telling is a free electron or electron from neighboring atom can fill this vacancy, which is called hole, and thus completing covalent bond. And this process is referred to electron hole recombination. Electron hole recombination. At a given temperature, two things will happen in the crystal. One, electron hole generation, electron hole recombination. And remember, at equilibrium, the number of generations, the number of recombinations must be the same. I am repeating again. The number of electron hole generation, electron hole recombination must be the same. Why? You know, at a given temperature, the number of free electrons per unit volume is a fixed value. So to make it a fixed value, these two must balance. And I just want to tell some more related to concept of holes. This is the identity of semiconductors. You won't see holes in conductors. Whereas in semiconductors, you will see holes. So this is whatever I am mentioning now is a very important term. Due to external energy, it can be the temperature of the body or when exposed to some radiation. Electron in the valency band shifts to the conduction. I will give clarity. The bond will break, or the electron which was the bonding becomes a free. So a vacancy is created in that bonding space, and this becomes a free electron. And this vacancy also behaves like a charge, positive charge. It will have affinity to accept an electron, which means it's positively charged. And the free electron, of course, is negatively charged. And this vacancy part is what we will term as hole. So they will also contribute to conduction. So I give some more, some more parameters, some more properties related to this hole. So please note this. My point is very clear, which was used in the last year. I am making it right now so that I want more time, more content, and in a lesser time of recording. So what are holes? Basically, they are imaginary charge carriers. True. And they are basically in valency band. They behave like a positive charge carrier. They are nothing but the absence of electron, and hence they are positive. See, remember, movement of electrons happen anyway due to temperature, due to the random motion and all that. Whereas the holes happens only when bond breaks. So therefore, movement of holes is due to the breaking and making of covalent bonds. Actually, its effective mass is more than electron. Its mobility is less than electron. Electron is free to move in any direction, but only in a specific location when the bond breaks, hole is created. That's the problem. Now I'll just give you a schematic diagram, the entire picture in a schematic diagram. Now you see here what is happening. You can see here. Here the bond breaks. You have a hole formed here and a free electron. Similarly, here also a bond breaks. Dots represent electron. White dot represents hole. Right. Here also you can say bond breaks. So you have 3 holes and 3 electrons. Reverse is also possible. Reverse is also possible. Right. Right. So hole acts as a virtual charge carrier. So in an intrinsic semiconductor, at a given temperature, electron hole generation rate is equal to electron hole recombination rate. Only then at a given temperature, the number of free electrons concentration will remain constant. So hereafter, whenever I am using Ne in the place of free electron concentration, or in other words, number of free electrons per unit volume. NH represents hole concentration, or in other words, number of hole per unit volume. Generally, Ne or NH usually refers to intrinsic carrier concentration. And Ne, NH is the same as N. Remember, this rule is applicable only for intrinsic, pure semiconductor. Intrinsic semiconductor. Right. So when the intrinsic semiconductor is connected externally to a battery, what happens? Frankly speaking, what happens here is holes will be drifted towards the negative terminal. Electrons will be drifted towards the positive terminal. In fact, in the conductor, it is the electron that moves. See, opposite to this, will be the direction of the current. You already know conventional current. But inside the semiconductor, the current is due to whole current plus electron inside. Already you have the condition in semiconductors. Current general formula is NEAVD. VD refers to drift velocity. Here, drift velocity of electron is not equal to drift velocity of holes. Because I said mobility of electron is not equal to mobility of holes. Drift velocity. So therefore, if I ask what is the total current, you will simply say Ne concentration, E A VD. I'm just using the same formula. But here in the place of VD, I need to write E. NH, E, A, VD, H. Someone having doubt in what is mobility? Mobility is defined as drift velocity per unit electron. So clearly the conductivity depends on, finally the conductivity depends on Ne, 1 minute. Here EA is common. NEVDE plus NHVDH. So this is current. So current is voltage by resistance. EA. NEVDE plus NHVDH. So with this, you can write a resistance is assuming a normal conductor type situation. Resistance is length into resistivity into cross-sectional area. Where rho L by A. NEVDE plus NH. So finally, A cancel. V by L refers to E. E. V by L, potential drop per unit length. Reciprocal of resistivity is conductivity. And this is EA NE mu E plus NH mu H times E. So by cancelling, you will have the conductivity as, even you won't have E also. Right. That's the deal. So now finally, mobility depends on the concentrations finally. You may ask me one question. At a given temperature, number of electrons jumping from valency band to conduction band depends on, this is a quantum mechanics output. So this can be given as N is equal to some constant A times T 3/2 e to the power of minus, this is energy gap by 2 kT. Here K Boltzmann constant. And this will be, you know this already, 1.38 into 10 to the power of minus 23 joule per Kelvin. Eg represents energy gap. A is a constant. A some constant. Material dependent. See, yet room temperature for every 10 power 12 silicon atoms, one electron jumps from valency band to conduction. Very pathetic situation. 10 power 12 silicon atoms, only one is live. In case of 10 power 9 germanium atoms, one electron joins from valency band to conduction. Right. Right. So this is all uh, related to a semiconductor in a purest form. All that which I have discussed is about a semiconductor in its purest form. Now we will proceed to semiconductor which is in the form of, which otherwise I can say semiconductor with some impurity. See, before that, I should define a term called doping. So, doping is a method where we deliberately, intentionally adds impurity atom to a pure semiconductor. What is the objective of this? To just increase conductivity of the semiconductor. Whatever that you are adding, that impurity atoms are called dopants. So therefore, which I am discussing right now is I am just mentioning what I have uttered right. So therefore, the addition of impurity will change the conductivity of the semiconductor. Now, this is a very important statement because over a period of time, you will forget what is the meaning of dopant. You know how the impurity is added? Impurity is added as 1 part per million. This is also called as a ppm, parts per million. For every 10 to the power of 6 pure atoms, for every 10 power now in this case, in this particular case, we should follow some rules. What are the rules? I'll mention that very clearly now. And this is a must and should condition. Whoever adds impurity, that they should accept these conditions. As mentioned, the dopant atom should take the position of semiconductor atom in the lattice. So you should select a material that should satisfy this condition. And number two, the presence of the dopant atom should not distort the crystal structure. It should not bring any physical changes in the structure of the crystal. Similarly, the size of the dopant atom should be almost the same as that of the crystal atom. Otherwise, it won't fit in that lattice mesh. The concentration of the dopant atom should not be large. I can say, I told you, 10 power 6 host one impurity atom, 1% of the crystal. It is to be noted that the doping of a semiconductor increases effect must be only on the electrical property, conductivity property. See, the concentration of the dopant atoms be very low. Doping ratio usually, this is the ratio. This is the ratio. 1 is to 10 power 6. 1 per every lakh to 1 per every 1,000, 10,000 lakh. Likewise. General followed is, madam. చెప్పండి. వాళ్ళు వర్క్ చేయించేసుకోండి. నేను క్లాస్ రికార్డ్ చేసుకుంటాను. వీళ్ళకి రైట్. ది ఇంప్యూర్, ది జనరల్, ఇదే కదా PPM. This is the general approach. There are two ways of doping, which is not at all your area of concern. Majorly, we go by diffusion. Of course, one is LI method, the other is majorly the diffusion is done, the impurity is added, doping is done by diffusion. Similarly, the size of the dopant atom, whatever it is, I told you, it should be almost close to the size of the crystal atom. Otherwise, remember, your intention is to change only the electrical property, not the structural property of the material. So these are very important observations I need to consider. And you may get questions like this in theory time, where you are madly confused and you will go with the wrong option. So I've given a very clear picture. Now, so to conclude, basically, what is happening in semiconductors? So this part is our prime focus right now. See, when you have a semiconductor material, till now, there is a pure semiconductor in the purest form called intrinsic semiconductor. Germanium, silicon are the best examples for this. And the basic identity of the intrinsic semiconductor is number of electrons per unit volume, number of holes per unit volume is the same, and that is what we call as carrier concentration. Whereas in case of intrinsic semiconductor, there is no doping. In case of a doped semiconductor is called extrinsic semiconductor. And it is again of two types, an N-type and a P-type material. Not refers to negative or positive. Please take this into consider. Whether it is N-type or P-type, both are electrically neutral. In a P-type, you will add a trivalent impurity. Sir, why trivalent impurity? Don't forget, your semiconductor valency is NS2NP2. You have only one option. Either go with NS2NP1 or NS2NP3. Otherwise, it won't fit. Clear? So if we are adding a trivalent impurity like gallium, boron, indium, aluminum, that comes under P-type category. Whereas if you add a pentavalent impurity, NS2NP5 configuration, phosphorus, arsenic, antimony, etc. These are called N-type impurity or N-type semiconductor. In N-type semiconductor, see, in pure semiconductor in purest form, number of electrons per unit volume, number of holes per unit volume is the same. Whereas in case of N-type semiconductor, domination is more by electrons than holes. Similarly, in case of the P-type material, domination is more by holes than electrons, which I have shown clearly in my basic structure. Now we will learn properly each part. N-type semiconductor. What exactly is N-type semiconductor? See, remember what is an N-type semiconductor? Pure semiconductor like germanium or silicon doped with a pentavalent impurity. Again, what are they? Phosphorus, arsenic, antimony, bismuth, etc. You will get an N-type semiconductor. No, the problem is what is happening just because of addition of this part. I'll represent it with. Now you see the crystal here. Here is your impurity. Here is your impurity. Now try to understand your impurity already sharing with this is 1 electron, 2, 3, 4. Remember, arsenic electron, 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 plus one more electron. And this fifth electron is loosely bound. This is loosely bound. And hence, this impurity atoms will donate that particular electron for conduction. And hence, this impurity is called donor impurity. Impurity. By donating this electron, it will become positive. And hence, after donating electron, it will become positive. And it won't move, by the way. Hello, it won't move. And hence, this will be called as, after that, immobile donor positive ion. So in N-type semiconductor, majority charge carriers are holes. minority charge carriers are electrons. I will explain you in band structuring also. I'll explain that in the band structuring also. Now, for example, you have valency band like this, conduction band like this. Valency band like this, conduction band like this. Now see, there is extra one more level. This is called a donor level. Remember, this is the fifth electron. I'm speaking about this electron. This is close to conduction band. For a very small energy, this will jump into conduction band. Remember, in the process of jumping, it is not creating any hole in the valency band. Tell me, at a given temperature, previously, number of holes in valency band is same as number of electrons in conduction band. But now in N-type semiconductor, number of holes is less than the number of electrons in the conduction. That is the difference. You do whatever you want. Now, mobility is changed. This will affect the conductor. Right? Now, please try to understand this is an N-type semiconductor. Whereas what is happening in a P-type semiconductor? So how do you get a P-type semiconductor? You will get pure semiconductor, silicon or germanium. When doped with a trivalent impurity such as boron, aluminum, indium. Sir, read it. Sir, read it. P-type semiconductor, you have original pure semiconductor doped with a trivalent impurity. What are boron, aluminum, indium, gallium, etc. So which makes a P-type semiconductor. Now see, I'll just show you the structuring of this system. See, in this, unlike see, here you notice the impurity is here. The impurity is here. The impurity is here. Because of the presence of the impurity, the impurity will share only 3 of its electron. One electron, which was supposed to here, is not available. And that deficiency behaves like a hole. Practically, there is no hole. But the deficiency of making covalent bond with other will behave like a. So it is ready to accept electron. This is ready to accept electron. So therefore, if you go through the band structure of this material, conduction band, valency band, now you will have an acceptor level. Don't forget, previously that is donor level. This is acceptor level. This acceptor level will accept. The acceptor level is somewhere over here. So an electron here will jump to acceptor level, not into the conduction band. But the problem is it has created a hole here, a hole over here. Because of the jumping, it creates a hole here. Now, what is the problem? The number of holes in valency band is greater than number of electrons in conduction. So that is what happening. And remember, like what I mentioned here, after accepting, this impurity is called acceptor impurity. And after accepting electron, it will become negative and same as immobile. So after donating electron, it will become positive. After accepting electron, it will become negative and it is immobile acceptor negative ion. That's a. So therefore, in this, what will happen? In this, majority charge carriers are holes, minority or electrons. Again, I am telling both are electrically neutral. That doesn't mean P means positive, N means negative. Right. So that is decided on the basis of the net charge. Don't forget. Now to conclude, all what I have done, I'll give it in one single picture, single diagram. All that what I have discussed now will be given in one diagram. Just please. Right. Now you see, you already have an idea about intrinsic semiconductor. Electrons jumped, holes are left, holes in valency band. The number of holes in valency band is same as number of electrons in the conduction band. So you can see the current is due to both holes as well as electrons. Suppose if this is how you have maintained potential difference. So holes will move in this direction, electrons will move in this direction, contributes current. Material is entirely neutral, remember. And number of electrons is same as number of holes, and current due to electrons is same as current due to holes. Right. Whereas in N-type material, as I mentioned, a special level is created here, it is impurity level. Actually, that I should say donor level, which is close to conduction band. As a result of which, you have only one hole created for this. This is the natural, this is called intrinsic process of creating electron hole pair. That is intrinsically generated electron hole pair combination. That is always here. But impurity level, that impurity excess fifth electron jump over to the conduction band, contribute extra electrons. So overall number of electrons in conduction band is more than number of holes in the valency band. And remember, the moment when these electrons are taken, are shifting into the what do you call, conduction band, the impurity will become positive. That the donor impurity becomes immobile positive here. That is the reason why you can see a positiveness inside symbol, mainly due to electrons. And number of electrons is much more than number of holes. Are majorly, where are you getting these electrons? The major contribution of electrons is due to the donor. So therefore, how many donor atoms per unit volume, you will have the same number of, almost same number of electrons per unit volume. Remember, entirely new. Majorly current is due to electrons. Majority electrons, minority holes. Same in case of p-type material. Just mentioned right now. See, these holes are not intrinsically generated. Remember, these holes are not intrinsically generated. They are due to the acceptor. The electrons in valency band will not jump to conduction band at that temperature, but they have sufficient energy to jump into the acceptor impurity. By accepting, it will become negatively charged. So see, accept చేశాక హోలే, అంత మునుపు హోల్, యాక్సెప్ట్ చేస్తే నెగటివ్లీ చార్జ్. సో ఇప్పుడు మీరు చెప్పండి, ఎన్ని హోల్స్ ఉన్నాయనేది నాట్ ఆన్ ద బేసిస్ ఆఫ్ ఇంట్రెన్సికల్లీ జనరేటెడ్. The number of holes is majorly due to the acceptor impurities. అందుకనే you have this term. Current is majorly due to holes and entirely neutral, of course, majority holes, minority electrons. This is how materials are classified. And last but not the least, there is one more term after which we will jump into the different discussions. This is a major part. There is an important term called mass action law, which I will discuss in my next class. Till this point, I will record and I will post. And please follow carefully.